witnessing a celestial body perform a sudden, impossible magic trick, transforming its very essence in real time. This is not a metaphor. It is the true story of interstellar comet 3I, Atlas. It arrived in our solar system as a silent, reddish-brown ghost, a chunk of cosmic rock appearing no more remarkable than a dusty asteroid. Then, as it approached the sun, it did the unthinkable. It burst into a brilliant, impossible green before developing a long, striking blue tail. What kind of alien chemistry allows an object to switch its fundamental color, not once, but twice? This is the mystery of the interstellar visitor, and the answer lies in a molecule so fragile, our sun literally tears it apart.
Interference levels confirmed minimal.
You are looking
Solar
through the
wind
lens of one of the
stabilizing.
world's
It's
most
quiet out
powerful
here.
telescopes. Perhaps the
Confirmed.
Gemini North
Charged
on
particle
Mauna Kea,
levels extremely low.
or maybe the Hubble Space
Solar
Telescope
wind nominal.
itself. And what you see defies the simple, predictable physics you thought you knew about these cosmic snowballs. It is Comet 3I Atlas, the third interstellar object we have ever confirmed passing through our neighborhood, following the enigmatic Oumuamua and the first interstellar comet, 2I Borisov. But this one is different. This is the moment of maximum enigma. The head of the comet, the bright fuzzy cloud known as the coma, is radiating a shocking, intense neon green glow. It's an almost sickly, ethereal luminescence that seems to defy the black vacuum of space. But here is the real puzzle that makes astronomers scratch their heads. Stretching away from this vibrant green head is not a green tail, but a long, straight, ghostly blue streamer, the ion tail. A green head and a blue tail simultaneously. It is a stunning, chemically complex portrait of alien matter being incinerated by our star. How can the same object, made of the same core materials, produce two such wildly different, vivid colors at the same time? And even more astonishingly, how did this interstellar comet, when we first saw it, appear red? I know what you are thinking. You are thinking of a traffic light, cycling through red, green, and blue. But this is not a simple filtering of light. This is a fundamental change in the object's physical state, a chemical explosion driven by heat and radiation. This is the moment where the seemingly inexplicable color change, from red to green to the blue tail, forces us to look deeper into the exotic chemistry of a body born in another star system entirely. To truly understand the shock of that green to blue spectacle, we have to rewind the clock to the comet's arrival. When 3I Atlas was first discovered in July of the year 2025 by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, it was not a vibrant green beacon. It was, surprisingly, redder than most comets we observe originating from our own solar system's Oort cloud. Imagine a chunk of ancient interstellar ice and dust, dark and cold, just entering the inner solar system. When we looked at it, the spectrum of light it reflected was dominated by the longer, redder wavelengths. You might be wondering, why is red significant? Well, the color of a comet, when it is far from the sun, is primarily determined by the dust and rock on its surface and in its nascent coma. This dust reflects sunlight. Most comets from our own system have a relatively neutral or slightly red-tinged dust, but 3I Atlas was noticeably redder. This particular hue suggested a few things to scientists. It could mean its surface was covered in a unique, highly processed type of organic material, perhaps tholins, which are dark, reddish, tar-like substances created by intense radiation exposure over billions of years in interstellar space. Or, and this is the fascinating part, it suggested that at that early stage, its activity was almost entirely dominated by dust, with very little gas sublimation happening. It was a dusty, reddish object, hinting that its composition, its very building blocks, might be different from the icy bodies we have cataloged for centuries. It was a red signal from a distant star system, a color that was unexpected for a classic ice-rich comet. This initial red phase sets the stage for the big question. What was the trigger that caused this seemingly dull red object to suddenly activate and undergo a dramatic kaleidoscopic transformation? The answer, as always in cometary physics, is the sun. As 3I Atlas plunged closer toward our star, the heat began to melt, or more accurately, sublime. The exotic ices locked deep within its nucleus. This is the moment the comet went from being a reddish, dusty artifact to a chemically active, glowing machine. The closer it got to the sun, the more volatile ices, like frozen water, carbon dioxide, carbon monoxide, and various carbon-bearing molecules, began to turn directly from solid ice to gas. This process is called outgassing, and it is what creates the comet's atmosphere, the gigantic, fuzzy coma. And within those gases lies the secret to the shocking color change. Now let us move from the enigma to the deep investigation. We need to dissect the science behind the green and the blue, molecule by molecule. The main culprit, the star of the show responsible for that intense, neon green aura around the comet's nucleus, is a simple yet highly volatile and reactive molecule: diatomic carbon. We write this molecule as C2. It is two carbon atoms bonded together. Diatomic carbon is an extremely unstable molecule that is abundant in cometary ice. When the comet heats up, the volatile parent molecules, larger, more complex carbon compounds, sublime into the coma. Once there, they are immediately bombarded by the sun's ultraviolet radiation. This energy is so intense it rips the parent molecules apart, freeing the diatomic carbon. So, what happens next? This is where the green light show begins. The diatomic carbon molecules absorb the sun's high-energy photons. This absorption excites the electrons within the C2 molecule, boosting them to a higher energy level. But those electrons hate being excited. They immediately want to drop back down to their stable, lower energy state. When they fall back down, they release that absorbed energy as a specific wavelength of light. And for the diatomic carbon molecule, that specific wavelength falls right in the green part of the electromagnetic spectrum. It is a process called fluorescence. It is essentially a giant, natural fluorescent lamp, powered entirely by our sun, and the gas is C2. This is a common feature of nearly all comets that get close enough to the sun. But the intensity of the green glow in 3I Atlas was particularly noteworthy, suggesting a rich abundance of carbon-bearing material, perhaps even more so than in many of our native solar system comets. But the mystery deepens when we turn our attention to the blue tail. If the comet is rich in carbon compounds that produce a stunning green, why does the long, straight tail, the part that stretches for millions of kilometers, shine a distinct, ethereal blue? The blue is the signature of the ion tail, and it tells us a completely different chemical story. The ion tail is not made of dust, or even the neutral gases of the coma. It is made of ionized gas atoms or molecules that have had an electron stripped away by the solar wind, giving them a net electrical charge. The key molecule here is the carbon monoxide ion, which we can call CO+. Carbon monoxide is another incredibly volatile ice found in comets. 3I on Atlas, being an interstellar object, showed a surprisingly high abundance of carbon monoxide, more than water, which is a significant compositional difference from most solar system comets. As the comet nears the sun, the carbon monoxide sublimates. Once in the coma, the solar wind, a stream of charged particles constantly emanating from the sun, strips an electron from the carbon monoxide molecule, turning it into the CO+ ion. These ions are then violently swept away from the sun by the magnetic field embedded in the solar wind. They don't just drift, they are accelerated, forming the long, straight, often dramatic ion tail. Just like C2, the CO+ ions also fluoresce when excited by sunlight, but their characteristic emission line is in the blue part of the spectrum. So the whole magnificent display is a two-part chemical opera. The green coma is the neutral gas of diatomic carbon, and the blue tail is the ionized gas of carbon monoxide. But we still have not addressed the most counterintuitive part of the whole phenomenon. We have established that the head is green due to diatomic carbon, and the tail is blue due to the carbon monoxide ion. But I want you to focus on the boundary between the two.
Dropping significantly,
You might be wondering,
indicating
if the
reduced
green
production
gas is
and
constantly
increased
streaming
destruction.
away from the full nucleus forming the coma, why does it not stretch out into a green tail alongside the blue one? Why is the green color confined almost perfectly to the compact region right around the nucleus? This is the spectacular, counterintuitive twist of cometary physics. And it is the moment where the sun, the source of all the light and heat, actively turns on its own chemical destruction machine. The reason you never see a long green comet tail is a process called photodissociation. Remember that the diatomic carbon, C2, is highly unstable. It is a fragile molecule, a transient byproduct of the sun's energy tearing apart larger compounds. As the C2 molecule is released and fluoresces green, it is simultaneously racing away from the nucleus at high speed.
Are far more resistant
But the
to
sun's
immediate
powerful
photodissociation
ultraviolet
than the
radiation
fragile C2
continues to bombard
molecules.
it. Within a relatively short distance, astronomically
The blue
speaking,
CO+
a few
ions are
tens
far
of
more
thousands
resistant
of
to immediate
kilometers from the nucleus,
photodissociation than
a
the
continuous stream of solar
blue
ultraviolet
CO+
photons
ions are
hits
far
the
more
C2
resistant to
molecule
immediate
with so much
photodissociation than the
force
fragile
that it
C2
breaks the
molecules.
bond between the two carbon atoms.
The blue CO+
The molecule
ions
is
are far
destroyed.
more resistant to
It
immediate
literally falls
photodissociation
apart
than the
into
fragile C2
individual
molecules.
carbon atoms, a process that happens in less than a day once the molecule is exposed to the full intensity of solar radiation.
The green is
Think of it
confined
this
because
way.
it is being freshly
The green
generated
light
faster
is
than
a
the sun can
short-lived
destroy it
chemical
only near the
flash.
nucleus.
The
Grand
diatomic
synthesis.
carbon is born.
The green is
It glows
confined because it
intensely
is
green
being
for a
freshly
few hours,
generated faster
and
than
then
the
the
sun can
sun's
destroy it
powerful
only
energy
near the
rips it
nucleus.
apart before it can travel far
The
enough
green
to
is
form a
confined because
visible
it is being
tail.
freshly generated
It is
faster
a
than the
beautiful,
sun can destroy it only
self-limiting
near the
chemical
nucleus.
reaction. This is the critical reversal of expectation. Our intuition tells us a plume of gas should stretch out indefinitely, but the physics of light and radiation dictate a rapid, violent end to the green glow. The green is confined to the coma, the atmosphere right around the nucleus, because that is the only place where the C2 is being freshly generated faster than the sun can destroy it. The blue tail, on the other hand, is made of the CO+ ions, which are much more resistant to this kind of immediate destruction, and are instead physically guided and accelerated away by the sun's magnetic field and the solar wind, allowing them to stretch out into that million-kilometer-long blue streamer. So the green-headed, blue-tailed spectacle of 3I Atlas is not a chemical contradiction. It is a perfect, time-stamped visual representation of two distinct chemical processes happening simultaneously. One process that creates a short-lived green flash, and another that creates a long-lived, magnetically driven blue plume. The mystery of the color change from red to green to blue, therefore, is not an inexplicable anomaly, but a beautiful textbook demonstration of cometary physics, intensified by the unique, alien composition of this interstellar visitor. Now we can tie all these threads together. The color change of Comet 3I Atlas, from an initial, surprising red to a vibrant green coma,
The
and
chemical
finally
difference
to a
between the
ghostly
coma and the
blue
tail is
tail.
clearly visible in the
Tells us a
side-by-side
story
data.
not just about
The
physics,
green C2
but about
peak
its
confirms the
origins in a
chemical
star
distinction.
system far,
The coma
far
shows
away.
significantly higher levels
The initial
than the
red
CO+
color
in the
was
tail.
our first clue that this object was unique. It hinted at a surface composition rich in complex, dark, red-tinged organic molecules, perhaps different from the pristine ices of our own Oort cloud comets. It was a dense, dusty signal from another star's protoplanetary disk. As it approached the Sun, that red, dusty signal was overwhelmed by the intense, sudden sublimation of its volatile ices. This transition was the chemical switch. The red dust was overshadowed by the brilliant green fluorescence of the newly freed diatomic carbon. The comet went from passively reflecting light to actively emitting it. The presence of the very strong blue ion tail, driven by the carbon monoxide ion, CO+, further confirms a crucial fact discovered through spectroscopy. 3I Atlas contains a significantly higher ratio of carbon monoxide to water ice than most of our solar system comets. This is the grand takeaway. The colors of 3I Atlas are a spectral fingerprint of its alien birthplace. Its chemistry is skewed toward carbon compounds, a composition that may reflect the unique conditions or the specific location where it formed around its parent star. So, what about the future color of this interstellar traveler? As 3I Atlas swings away from the Sun, moving back out into the cold, dark reaches of space, the process will simply reverse. The solar heating will decrease dramatically. The sublimation of the volatile ices, the carbon monoxide, and the parent molecules that create the diatomic carbon will slow down and eventually cease. The green glow, that beautiful flash of C2, will be the first to fade. As the production of the diatomic carbon slows and the Sun's radiation continues to destroy what is left, the green coma will shrink and dim until it disappears entirely. The blue ion tail, the CO+, will also fade as the solar wind has less and less gas to ionize and sweep away. The comet will revert to its initial state, a cold, dark, reddish object. It will become a silent, dusty nucleus once more, reflecting only the faint, distant sunlight. Its color will be determined solely by the dust and the surface material of its nucleus. It will then continue on its hyperbolic trajectory, leaving our solar system forever, carrying the memory of its brief, spectacular color show, red, green, and blue, into the vast, endless night between the stars. The story of 3I Atlas is a powerful reminder. It shows us that a comet is not just a chunk of ice. It is a time capsule, a spectral code written in light. By decoding its colors, the red of its ancient dust, the green of its volatile carbon, and the blue of its ionized tail, we are not just solving a mystery. We are reading the chemical history of an entire distant star system, one brilliant, fleeting molecule at a time. And that, truly, is the most profound color change
Sublimation
of
rate
all.
unstable. Approaching critical threshold. Warning. Data integrity compromised.